Welcome back to Math 104. A voter walking out of the polling booth is selected at random and says that he voted against the referendum. What is the probability that he is an independent? We first note that this is a conditional probability. Before we ask about the probability that he is an independent, we have prior information that he voted against the referendum. That means we already know that this voter is one of these 490 voters. The probability that he is an independent is therefore 30 over 490. That is, the probability of I given S complement equals 30 over 490. Here's another example. A computer retailer obtains all its laptops from 3 factories, A, B, and C. Some of the laptops work properly, while others are defective. 90% of those from factory A work properly, 85% from factory B work properly, 80% of those from factory C work properly. 25% of all laptops come from factory A, 30% of all laptops come from factory B, and 50% of all laptops come from factory C. Let's first ask about the given information which of these percentages, which we can think of as probabilities, are conditional probabilities, and which are unconditional. These last 3 pertain to all laptops, and therefore this is unconditional information. Each of the other percentages is a percentage of just what comes from one particular factory. Therefore, this is all conditional information. If we drew a tree, let's think what it would look like. As always, the first branching is based on unconditional information, so that has to be the branching into factory A, factory B, or factory C. Within each factory, there is a further branching into works or doesn't work. Works or doesn't work, works or doesn't work. Again, we can label edges of the tree with probabilities, but let's go straight to the table. Let's work with an ideal dataset of size 1000, and then we can think about whether we could have gotten away with a smaller sample, with a smaller sized ideal dataset. Let's first work with an ideal dataset of 1,000 computers. We work first with unconditional information. 20% of all laptops come from factory A. So 20% of these 1,000 laptops in this perfectly representative sample of them, that's 200 laptops, come from factory A. 30% of all laptops come from factory B, that's 300 of them, and 50% of all laptops come from factory C, that is 500. Within factory A, now we apply conditional information. 90% of those from factory A, that's 90% of 200 equals 180. Those are the ones that come from factory A and work properly. That leaves the remaining 20 from factory A that do not work properly. From factory B, 85% work properly. 85% of 300, that's 0.85 times 300, equals 255. That leaves 45 computers from factory B that don't work properly. 80% from factory C work properly. 80% of 500 equals 400. That leaves 100 that are from factory C and don't work properly. So now we've applied all of our given information. We get the benefit of this work. We can easily sum the columns. There are 835 laptops that work properly from whatever source. 835 laptops total work properly. That leaves 165 laptops that do not work properly. Now we are all set up to answer probability questions. A laptop is selected at random. What is the probability that it works properly? Since the phrasing is that a laptop is selected at random, that means a laptop is selected at random from the entire collection of 1,000 of them. What is the probability that it works properly? There are 835 properly working laptops in this ideal data set of 1,000 of them. Therefore, there is a 0.835 probability that a randomly selected laptop works properly. If a randomly selected laptop works properly, what is the probability that it was made by factory B? Pause a moment and think, what is the answer to this question? Given that the laptop works properly, that is the known information about the laptop, we ask, what is the probability that it comes from factory B? Thus, out of these 835 properly functioning laptops, 255 of them are from factory B. That is an approximately 0.3054 probability. If a randomly selected laptop was made by factory B, what is the probability that it works properly? Let's be careful. What are we conditioning on, and what are we ultimately asking about? If a randomly selected laptop was made by factory B, given that it was made in factory B, we now ask, what is the probability that it works properly? These two probabilities are not the same. We are conditioning in opposite orders. We could work from here and compute the probability to be 255 over 300. Since we are conditioning on the event B, our probability is out of 300, hence 255 out of 300. Or we could note that this is actually one of the given probabilities in the original information. Not only are these two probabilities not equal to each other, they are also dramatically different from each other. Here is our last example of this method. An insurance company compiles the following data on drivers and the accidents they had last year. These are made-up data, but in practice, insurance companies compile much more detailed data than this. Let's just look at age versus likelihood of accidents. Based on the data they collected, 23% of the population were under 30. 15% of them had accidents last year. 18% of the whole population was between 30 and 39. 9% of them had accidents last year, etc. This is presenting the information in a slightly new way. To understand what's going on, let's ask, do the entries in the percent of population column represent conditional or unconditional probabilities, and how can you tell? These are unconditional probabilities, because each one is a percentage of the entire population. Or in probability terms, there is a 0.17 probability that a randomly selected driver from the entire group of drivers, or the entire population, was between 40 and 49. Do the entries in the percentage of group who had accidents column represent conditional or unconditional probabilities, and how can you tell? These are conditional probabilities. Each percentage is not a percentage of the entire population, but only of a certain subset of the population. Now we have enough different categories that even the given information is presented in a table. If we were to draw a tree, there would be 1, 2, 3, 4, 5 edges in the first branching. Under 30, 30 to 39, 40 to 49, 50 to 59, 60 and over. And then from there would be a double branching each way, based on had an accident or didn't have an accident. Although the tree is worth understanding conceptually, by now it's really a mess, and we want to work just with the table. Let's look at a total population of 100,000 drivers. Out of 100,000, 23% are under 30, so this is easy to work out. 23,000 were under 30 in this ideal data set of 100,000. Then 18,000 were between 30 and 39, 17,000 between 40 and 49, 15,000 between 50 and 59, and then 27,000 60 and over. 15% of these 23,000 were under 30 and had an accident. That's 3,450 drivers. The rest of the under 30 group, all 19,550 of them, did not have an accident. Within the 30 to 39 group, among these 18,000 who were in that age group, 9% of those 18,000, namely 1,620 drivers, were 30 to 39 years old and had an accident. The remaining 16,380 were in their 30s and did not have an accident. Before going on to the next video, fill in the remaining entries in this table.